Working with combinations, there are cases where we need to look at different subsets of combinations and the cases that situate themselves within there. So if we're given a set of elements, we can break that set down into multiple subsets with varying numbers of elements. Anywhere from 0 elements, which is called the null set. So this here is the null set. Or 1 item, 2 item, 3 item, or so on until we fill up the entire set. So if we're given the set 1, 2, 3, 4, then all the possible subsets are the null set, the set where we have 1 item, and so we could have either a 1, a 2, a 3, or 4, so there's 4 options there. The set where we have 2 items, and these are all the pairings of items that we can get. And again, because we're related to combinations, the order doesn't matter. The set where we have 3 items, so 1, 2, 3, 4 different possible sets have 3 items, and then finally the set of 4 items, which is just the entire set, and there's only 1 option. So here we have all our sets, and if you were to look at any of these in terms of a combination, the null set, we have 4 items, we want to choose 0. How many ways can we choose 0 items? 1 way. The next set, the set of 1 item, so we have 4, choose 1, so that equals 4. And then the next set, we have 4 items, we're choosing 2, so there's 1, 2, 3, 4, 5, and 6 combinations, and 4 choose 2 is equal to 6, and then 4 choose 3 is equal to 4, and 4 choose 4 is equal to 1. So each of these pairs off with a combination, and thus, if we want to count all the subsets, it's the number of items in the set, choose 0, choose 1, choose 2, choose 3, choose 4, and all the way up until we get to choosing the entire set, and we just add all those up. Or another way we can look at this sometimes is to look if we are including an element or not. So are we including the 1, or are we not including the 1? Are we including the 2, or are we not including the 2? Are we including a 3, not including a 3? Are we including a 4, not including a 4? And so that way, if we look at including or not including elements, then we can calculate it by using, when they're binary options, we have it or don't have it, is when this works, 2 to the power of n. Often, we don't include the null set, so we will do 2 to the power of n minus 1. So we'll look at an example of using this. This is often considered the indirect method of calculation because we're finding the total minus the situation that we don't want. So in this case, Timmy is painting. He has red, blue, green, and yellow paints to use. How many different combinations of colors can he choose? So we can choose to use just red, just blue, just green, just yellow, or red, blue, blue, green, so on. Or he can choose 3 of them, or he can choose to use all 4. So using combinations, he can choose to use 1 color, or he could choose to use 2 colors. He could choose to use 3 colors, or he could choose to use 4 colors. And 4 choose 1 is 4, 4 choose 2 is 6, 4 choose 3 is 4, and 4 choose 4 is 1. That tallies us up to a total of 15. And just to connect it back to the original, if we had a set of 4 elements, all the possible subsets are 16, but because we want to have some sort of color that we paint, we are not going to include the null set, so 16 minus 1 would be the 15. Using that in the indirect method, we can choose to use each of the colors, so we can choose to use blue or not. So if this is blue, this is red, yellow, and green, we could choose to use either one. So there's 2 options for each color. Use blue or not use blue. Use red or not use red. Use yellow or not use yellow. Use green or not use green. And then again, we don't want to use the set where we choose nothing, the null set. So if you look at that, 2 times 2 times 2 times 2 is the same as 2 to the power of 4 minus 1, which is 16 minus 1, or 15. It's the same answer. So if we're in a binary option of using something or not using something in a set of items, then we can use the individual combinations, but again, if it gets too big, like if there was like 15 paint colors, you'd have to do 15 combination calculations. You could do 2 to the power of 15 minus 1. It'll be a lot easier. So that's the indirect method of using it. When we look at the cases, situations with cases, so we might have a situation where we want to have, at least this many items, or at most this many items. So we're using cases for this. So when we are using cases, we sum up the various cases. In the example, the game of hearts is a card game that uses the entire deck. Given a hand of 13 cards, how many would contain at least 2 hearts? So the different cases here is that we could have a hand with 2 hearts, a hand with 3 hearts, a hand with 4 hearts, a hand with 5 hearts, a hand with 6 hearts, 7 hearts, 8 hearts, 9 hearts, 10 hearts, 11 hearts, or 12 hearts, or 13 hearts. That's 11 different cases. That's 11 different calculations. That's 11 different chances to make an error. Something easier might be to look at the total number of hands that we could have and then just get rid of the 2 cases we don't want. We only have 2 cases that we don't want. The case of not having any hearts and the case of having 1 heart. So let's do it that way. So the total cases, or the total hands, minus 0 hearts hands minus the hands with 1 heart is what we're going to do. So the total number of hands you can have if you're picking 13 cards is 52. Choose 13. Hands with 0 hearts, so now we're only left with 39 cards out of the 52. We can have the 13 the 13 clubs, spades, or diamonds, and so that's 39. Choose 13. So that would be 0 hearts. And then if we have a hand with 1 heart, we need to choose the heart we're going to have in the hand. So we have 13, choose 1. We're selecting 1 heart in our hand, and we're going to multiply that by the number of hands, or the remaining cards in the hand. 39, choose 12. So 39, choose 12 is going to be a 12-card hand not having hearts, times the single heart that we're adding into it. And which of those hearts? There's 13 different options. So we can calculate that all out, and when we work it out, you're probably going to get an exponential number. In my case, it's 5.760507,675 times 10 to the power of 11, which is not exact. It's approximate. The actual answer for this, and I've done this on a computer, I've done this on a calculator, and it comes out both the same. And in many cases, with these really wildly long numbers, you will have these exponentials. So it's 5.76057,675 times 10 to the power of 11. Your calculator might use an E11, which that E means 10 to the power of 11. So that there, the exact number, so that's approximate, the exact number is 5.76057,675, not 5, 7,488, I believe. It's either 488 or 448. I think it's 488. The answer is in the textbook. This is a question from the Your Turn in Example 2 on page 119. So it's pretty darn close, but it's a pretty big number. So we are, again, working with really large possible combinations when we're working with even just numbers as big as 52, choose 13. Now, that was, again, looking at the total cases, subtracting the cases where we had no hearts and the cases where we had 1 heart, meaning that we now have all the cases where there are 2 hearts, all the cases where there are 3 hearts, 4 hearts, then 5 hearts, then 6 hearts, all the way up to 13. So this was a little bit quicker. Otherwise, we would have had to do these calculations 11 times. Now, in the case where we want at least 10 hearts, well, now we just have the case of 10 hearts, 11 hearts, 12 hearts, and 13 hearts. Now there's only 4 cases that we want So it'll be easier to actually calculate the 4 cases we want rather than the ones we don't want. So in this case, there's less to do if we do it directly. So the hand with 10, so we have 10 hearts, then 11 hearts, 12 hearts, and then a full hand of hearts. Well, hands with 10 hearts. So we're going to choose from our hearts 13, choose 10 hearts times, 13 hearts, choose 10, times 39 cards left that are not hearts, choose the 3 remaining. So there's 10 hearts, plus when we choose 11 hearts, 13, choose 11 hearts, times 39, little neater here, 39, choose 2, plus 13, choose 12 hearts, so there's picking our 12 hearts, times 39, choose 1, and then a hand of fully made of hearts is 13, choose 13, or just 1, and there'll be no other cards to pick. So we calculate that all out, and we get a really big number of 2,672,060. So 2,672,060 possible hands have at least 10 hearts. So there's only 4 cases here where there was 11 cases here, thus the vast change in number. Finally, we're looking at choosing and arranging. So in some cases, we need to choose some items and then we need to subsequently arrange those items. So if we have the situation where we have a class of 10 boys and 18 girls, 3 boys and 4 girls will be chosen to go on a trip. How many ways can the chosen students be arranged on the bus? So we're choosing some boys and girls to go on a trip first, and then given those choices, we're going to see how many ways we can arrange them to be seated on a bus. So choosing 3 boys from 10, so 10, choose 3 will be our boys going on the trip, times 18 girls, choose 4 of them. And now this is the number of students going on the trip, but we also now have to take those 7 students on the trip and we have to arrange them on the bus. So if we're arranging them on the bus, now order matters. So when we're choosing who's going, it doesn't matter, but the way we put them on the bus is going to matter, because sitting at the front, the back, the middle, different seats, that makes a difference. So that's a permutation. So we have 7 items, and so we're arranging 7 items 7 ways, 7p7, or just 7 factorial would be another option there. Again, remember 7 permutations of 7 items, or 7 items, permutations with 7 items is 7 factorial. So we can take that and calculate that out. We have a total of 1,850,688,000. So we put some commas in there, and that is 1,850,688,000 different ways of selecting 3 boys from the total of the 10, 4 girls from the total of 18, and then arranging those 7 kids that we choose on the bus. So really, really big number. So when you're working with your permutations, your combinations, look at the different possible cases at times, and if it is important to compare the outcomes we want to the outcomes we don't want, see which one's easier to calculate. It might be less work This will take a little bit more time to kind of get through at times. So take your time doing the questions when you're doing these kind of problems.